Okay, so this is Chapter 4, Sections 1 and 2. Your homework is to take notes with all the examples and definitions and to answer the questions at the end. And what we're going to talk about here is exponents, and in particular exponents where you have a positive integer as your exponent. And so the first thing we want to do is we want to define what an exponent is. And an exponent is a shorthand way to write repeated multiplication. And that repeated multiplication is of the same number. And that number is called a factor. Okay, now when we look at an exponent, this number is called the exponent. It's also referred to as the power. And this number is referred to as the base, which is also the factor. Okay, that power tells us how many times we multiply the base. Okay, so for example, 2 to the 5th, you're going to multiply 2 by itself 5 times. Now, when we have common bases, what this means is that we have 2 different exponent expressions with the same base. So our base is the bottom number. So for example, if I had 5 to the 3rd and 5 to the 15th. These would be common bases because they have the 5 in common. Now when we have exponent terms with common bases, we have some rules we can follow. Now the product rule, if I write it symbolically, is x to the m times x to the n is equal to x to the m plus n. So when I multiply common bases, you add the exponents. Okay, and here's why that works. Let's say, for example, I have 2 to the 3rd, and I want to multiply that times 2 to the 6th. Well, if I expand this out, 2 to the 3rd gives me 3 2's, times 2 to the 6th, and if I count this up, I now have 9 2's, 2 to the 9th. Well, I could skip all this and just add my exponents. 3 plus 6 equals 9. So here's some examples. I have 5 squared times 5 to the 3rd. That's 5 to the 2 plus 3, which is 5 to the 5th. Now on this instance, I have some constant terms out front and then my common bases. So what I need to do is I'm going to multiply 4 times 3. And then I'm going to multiply x to the 3rd times x to the 4th. I have 2 things that I need to do here. So that's going to give me 12 x to the 3 plus 4, which is 12x to the 7th. You can see here I have a couple things, and I want to identify my common bases. I have 3 to the 4th and 3 to the 3rd. So what I'll do is I will multiply 5 times 7, here and here, and then I'll multiply 3 to the 4th times 3 to the 3rd, and that's going to give me 35 times 3 to the 7th. And now I want to figure out what 3 to the 7th is. So if I look at a scientific calculator to do an exponent that's not a squared, I use this little triangle symbol here, which is called a caret. Zoom in. That's the symbol right there. And so what I'll do is I'll put in, 3, then the caret, and then 7, because my exponent is 7, and that's 2,187. And then I multiply that by 35. So that's 76,545. Okay, now, careful note, do not confuse this with addition. If I'm adding common bases, in this instance, my exponents match, so this is like terms. And so I add the 4 and the 3, and the exponent doesn't change. Now if I have unlike terms, so for example I had 4x to the third and then I had 3x squared, well, this is already simplified and I can't do anything with it. So just be really careful when you add common bases with the same exponent, the exponent does not change. It only changes when we're multiplying. Okay, the next rule we have is the quotient rule, which quotients are division, and if when we multiplied we added, the opposite to that would be when we divide, we subtract. So if I have x to the m divided by x to the n, I take that and I say m minus n. So, for example, I have x to the 8th over x to the 4th. This is x to the 8 minus 4, which is x to the 4th. 5 to the 7 over 5 to the 3rd gives me 5 to the 7 minus 3, which is 5 to the 4th. And then if we wanted to simplify that even further, I plug that in, 625. When I have constants in front, I divide or simplify this part. So I want to look at that kind of separately. I want to look at that as 10 over 2 and x to the 10th over x squared. I take each part separately. So the 10 over 2 gives me 5. The x10 over x squared, 10 minus 2 is 8. Here I have negative 12 and 27. So if I write these separately, okay, 12 and 27, 12 does not divide by 27. Both 12 and 27 will divide by 3. So I'm going to simplify that fraction by dividing by 3. So that's going to give me negative 4 over 9. Now here I have no exponent, and when I have no exponent, there's a little invisible 1, because anytime you have anything to the power of 1, it equals itself. So this x has a little tiny 1 over it, so I have 6 minus 1, that's x to the 5th, and that's going to come up here in the numerator. So I have 4x to the 5th over 9. This next example, I have 3 different parts to take into account. Now, remember there's like a little invisible 1 on that x. 12 and 24 both divide by 12. So I have negative 1 over 2. And I'm not putting the 1 in here, and you'll see why in just a second. I have 6 minus 1 on the x's, so that gives me x to the 5th. And I have 5 minus 3 on the y's, so that gives me y squared. So I have negative x to the 5th y squared over 2. Now sometimes the exponent in the denominator is greater. Now we're still going to subtract, and this is going to give me x to the 2 minus 3, which is x to the negative 1. We're not allowed to have negative exponents, and so it goes to the denominator. Well, an easier way to do that is to take the denominator, that gives me 4. The x to the 5th is bigger than the x to the 1st, so I know that 4 needs to go in the denominator. So I'm still subtracting, I'm just subtracting the bottom minus the top this time. And whichever one is bigger, that's where your answer goes. Here I have a little invisible 1. I have 5 minus 1, which is 4. So that's 1 over 3 to the 4th. And if I want to know the exact number, it's 1 over 81. 15 is going to stay 15. And then I have 6 minus 2, or 2 minus 6, which is negative 4, or 4. So the 4 goes in the denominator. And here again I have multiple things happening. I take the 21 and I divide it by the 7. 5 minus 2 is 3. And then here the denominator is larger, so I have 9 minus 3 is 6. Okay, our next rule is the power rule. And when we were talking about power rule, we're taking a power to a power. So if I have x to the m and I raise that to the power of n, and multiply the two together. Now, the difference between this and the product rule I have two bases. Here I have one base with two exponents, so that can help you to keep track. Okay, so here's an example. I have 2 times x to the third to the fourth. Now, this fourth is not touching the 2, so it's not 2 to the fourth, it's just x to the third to the fourth. So I'm going to multiply 3 times the 4, and that's going to give me 2x to the 12th. Here, same thing, the 5 is only touching the x squared, not the 3. So that's 3x to the 10th. Here I have a negative 2, x to the 8th to the 9th, so I multiply 8 times 9, and that gives me negative 2x to the 72nd. Now I want to do a little note. If I have a negative 4 squared outside of parentheses versus a negative 4 squared inside the parentheses. Now, negative 4 and the negative is not in the parentheses. The 2 is only acting directly on the 4. It's not acting on this negative, so that's going to be negative 16. Here, the 2 is acting on the 4 and on the negative. This is negative and then 4 times 4, whereas this is negative 4 times negative 4, so that's going to be positive 16. If I have an odd exponent, same idea. If the exponent's not touching the negative, it's not acting on it. So this is going to be 4 times 4 times 4. That's going to give me negative 64. Here, it is going to act on the negative, but I have 3 negatives being multiplied together, so negative times a negative is a positive, times another negative is going to give me a negative. So a general rule for negatives is if I have a negative number to an even exponent, and that negative is in the parentheses, I'm going to have a positive answer. And if I have a negative number to an odd exponent, I'm going to have a negative answer. Now to take that one step further, we have the power of a product, which means I have a product inside the parentheses being raised to a power. And what happens here is that both things inside the parenthesis, or if there's more than 2, everything inside the parenthesis is going to get that exponent multiplied by it. Now, remember, if there's no exponent here, there's little invisible ones. So I get x to the n, y to the n. Here's another example. I have 3x to the third y, and then the whole thing is being squared. So I'm bringing in this exponent to everything. So it's going to give me 3 squared, x to the 3 times 2, and then y to the 1 times 2, because there's a little invisible 1 there. So that's 9, x to the 6th, y squared. Here I bring in this third. That's going to give me 4 to the third, x to the 3 times 3. So that's 64 x to the 9th. Here I bring in this 4. So that's 2 to the 4th, x to the 5 times 4. So that's going to be 16x to the 20th. And again, bring in this 5. And I have 3 to the 5th, x to the 2 times 5. So 3 to the 5th is 243. And that gives me x to the 10th. Now, again, I did say no matter how many items were inside the parenthesis, bring the exponent to all of them. 6 squared is 36. 3 times 2 is 6. 2 times 2 is 4. 4 times 2 is 8. Now, again with the addition versus the multiplication, 4x squared squared is different than 4 plus x squared. For 4x squared squared, I can bring in this squared like that. And that'll give me 16x to the 4th. However, if I have an addition or a subtraction in there, this is 4 plus x squared times 4 plus x squared. I'm squaring the whole thing, so I have to multiply it by itself. And we're going to go over this later. Okay? Okay, the next rule is the 0 power rule. And this rule it's very easy. Anything to the power of 0 equals 1. So x to the 0 equals 1. 3x squared, y to the 5th to the 0, 1. 9 to the 0, 1. 14 to the 0, 1. X to the 0, 1. So I have 1 plus 1 plus 1 half. 3 times 5 to the 0, that's 3 times 1, that's 3. All of this to the power of 0 is 1. 9 billion to the power of 0 is 1. Anything to the power of 0 is 1. Okay, the next thing we have is the power of a quotient, which is very similar to the power of a product. This works in the same way. If I have a quotient, I'm going to use y on that one, and I raise that to another power, so let's just say p. This will be x to the m times p over y to the n times p. This exponent here gets multiplied into both the numerator and the denominator. So here's an example. I'm going to start with actually a simpler example. If I have x to the 5th over y to the 7th, and I square that, I'm going to do 2 times 5 and 2 times 7. So that's x to the 10th over y to the 14th. Here I have multiple terms inside. So I take negative 2 to the 3rd, and then multiply 3 times 4, and 6 to the 3rd, and 2 times 3. So this is going to be negative 2 to the 3rd, x to the 12th, over 6 to the 3rd, y to the 6th. Now I need to simplify the 2 to the 3rd. Now it's going to be negative because I have an odd exponent. So that's negative 8, x to the 12th, and 6 to the 3rd is 216. Now both 216 and 8 divide by 8. So I get negative x to the 12th over 27 y to the 6th. Here I'm going to take the squared to the 9, to the x, and to the y, and I'll get 9 squared x squared over y squared, which gives me 81 x squared over y squared. So just remember, whenever you have an exponent on the outside of parentheses, every single thing inside the parenthesis gets taken to that exponent. And here we're going to combine some rules. We've got some multiplication going on, some that exponent goes into those. So this gives me 5 times 3 to the 4th, which is 81, x to the 8th, over 6, x, 10 and 3, x to the 10th, so that's going to be x to the 13th. 5 times 81 is 405. Okay, 405 does not divide by 6 evenly. However, they do both divide by 3. So I'm going to get 135 over 2. And then I have 8 and 13. 13 is larger, so I do 13 minus 8, which is 5. And that goes in the denominator. So here we have another example where we have a whole lot going on. When I have parentheses and other parentheses, I start inside first and then work my way out. So the first thing I need to do is take these 3 there and this 2 here. Okay, 3 to negative 2 gives me negative 8, and then that gives me x to the 6th. 3 squared is 9, x to the 8th, and that whole thing's going to be taken to the 3rd. Now I'm going to worry about this. 3 times 8 is negative 24. 2 times 9 is 18. Now I could go 2 ways with this. I can either bring this power in and then reduce, or I can reduce and then bring the power in. It's actually going to be easier to reduce first and then take things to the power. So 24 and 18 both divide by 6. And then I have a 6 and an 8. 8 is larger, so I have x squared in the denominator. Now I bring in this last final power of 3, and I have 4 to the 3rd, which is 64, and that's going to be negative because I have an odd exponent. And then 3 to the 3rd is 27. And x squared to the 3rd, I have 2 times 3, so I get x to the 6th. Last one of these examples, again, I have a lot going on. So I look and see what I have. I have this squared right here. So I need to do that first. And I bring that 2 in here, and here, and here, and here. I'm going to leave everything else alone for right now. Two squared is 4. X squared squared, that's 2 times 2 is 4. 4 times 2 is 8. And then that little invisible 1 times 2 is 2. And I just wrote down everything else exactly how it was. Now I'm going to multiply these things together. So I'm going to multiply the numerator, and then I'm going to multiply the denominator. And when I do that, I'm going to multiply like times like. So 6 times 4 is 24. X to the 4th times x to the 4th. I'm going to add those exponents. So that's 8. Y to the 3rd times y to the 8th. So 3 plus 8 is 11. And then I have a z squared. In my denominator, 2 times 9 is 18. X to the 4th times x. That's the little invisible 1 there, so it's 4 plus 1, that's 5. Y squared times y, that's 2 plus 1, so that's 3. And then z to the 4th, and then I still have that squared outside. Now I'm going to reduce what's inside. 24 and 18 both divide by 6. 8 minus 5 is 3. 11 minus 3 is 8. 4 minus 2 is 2. And then I square everything. 4 squared is 16. 3 times 2 is 6. 8 times 2 is 16, 3 squared is 9, and 2 times 2 is 4. Okay, section 2 is on negative integer exponents and scientific notation, and we kind of touched on negative integer exponents when we were doing quotient rule. But basically, the rule is this. If I have a negative exponent, first of all, they're not allowed, except in scientific notation. Okay, so if I have a negative exponent, I put it in the denominator. If I have a negative exponent in the denominator, I put it in the numerator. So if it's a negative exponent, you flip it around to the other side. So if it's negative and it's by itself already, it goes in the denominator. If it's negative and it's in the denominator, it comes out of a fraction, or goes in the numerator. So here's some examples. 2 to the negative 3 is 1 over 2 to the third, which is 1/8. 3x to the negative 2. That negative 2 is only acting on the x, so the 3 stays up top, and x squared goes to the bottom. Now here, the negative 2 is acting on both the 3 and the x. So it's like this, which gives me 1 over 9x squared because I square the 3x. Here I have a negative exponent in the denominator, but it's only acting on the x, not the 2. So I bring that up top and leave the 2 below. Here I have a negative negative exponent in the denominator, and that brings the whole thing up top. And then 2 to the third is 8, and 8 times 5 is 40. Here I have a negative and a negative, so I'm going to flip them because this negative 6 needs to go downstairs and this negative 3 needs to come upstairs. But then I have common bases, so I have to subtract 6 minus 3, and I have a 3, sorry about that, in the denominator. Negative 4 and negative 8 can be reduced. They both divide by 4. That's a negative 1. And then x to the 6th goes to the denominator. The x squared goes to the numerator. Then I can reduce that. 6 minus 2 is 4. Here, this whole thing is being taken to the negative third, so I need to drop the whole thing into the denominator. Then I take everything to the power of 3. So that negative 2 to the third gives me negative 8. X to the third, y to the negative 9. Now that negative 9 needs to come upstairs. Also, this negative needs to come out front. If I have two negatives, I make it positive, but if I have a negative then in the denominator, I just bring it to the top or out front. So that'll give me y to the 9th in the numerator, and then 8x to the third in the denominator. Okay, last example like this, we have negative exponents. This whole part is going to come downstairs. This was already down here, so it stays. Then this whole thing is going to come up top. Then I'm going to square each of these. Now I have these negative y's, so they're going to have to switch places. Like that. Then I multiply these two together. 6 times 4 is 24. That's x to the 9th, y squared. Now I have x's and y's in the numerator and the denominator. So I have 10 minus 9, which is 1, 6 minus 2, which is 4, and that 24 stays in the denominator. Okay, here's kind of an example problem of when you might need to use this. The level for the f-stop, which is f, on a camera is equal to the product of the focal length L and the diameter of the aperture D raised to the negative first power. Okay. F-stop, F, is equal to product of focal length and the diameter raised to the negative first power, but we don't have negative exponents. So I get F is equal to L over D. Oh, that was part B. Okay, if the diameter of the aperture is 100, so that's D, so that goes in the denominator, and the focal length is 200, that goes in the numerator, the f-stop would equal 2. Okay, scientific notation is a shortcut or shorthand, and that is to write very, very large numbers or very, very small numbers. And by that we mean long decimals with lots of zeros in front usually. If we have a very, very large number, we have a positive exponent. And if we have a small number, we have a negative exponent. Okay. So for example, a large number might be written like that, and a small number, if this was a long decimal, would be written like that. So, to convert to scientific notation, the exponent symbolizes the number of decimal places moved. Because when you multiply or divide by 10, you move decimal places. So this is if you multiply by 10, these are if you're dividing by 10. So what we do is we count. I'm going to take the decimal from there and I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's 12 spaces. And we always go after the first number that's not a 0. Okay, and that's the first number reading from left to right. So in this case, 5 is the first non-zero number. So we move to the after 5. Now, we keep 2 decimal places. So I have 8, 6, 5. This 5 would round the 6 up to a 7. And then that's times 10, and the number of spaces is my exponent. So let's try another one. I'm going to move from here. 1, 2, 3, 4, 5, 6, 7, 8. Now, I don't have to write the 0, so it's just 2.3 times 10 to the 8th. You only ever keep 1 or 2 decimal places. Two is standard, 1 if the next one would be a 0. Now when we do decimals, we're doing the same thing, but we're moving this way. So here we were moving this direction, here we're going to move that direction, and I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. That's the first number that was not a 0. So this is going to be 2.3 times 10 to the negative 9. And it's negative because this was a long decimal. Here's another example. 1, 2, 3, 4, 5, 6 to the first non-zero number. keep 2 decimals, and my exponent is -6 because I moved 6 spaces. Now, if we can take a big number and convert it to scientific notation, we can take scientific notation and convert it to a standard number. We have a positive exponent, so I know we're going to move the decimal this direction because of the positive exponent. Down here I have a negative exponent, so I will move the decimal that direction. So if I have a positive exponent, I move to the right. And what I usually do is I need to move 8 spaces. So I start counting. 1, 2, 3, 4, 5, 6, 7, 8. And what I've done is I've moved the decimal 8 spaces. So again, write down that first number. The first number doesn't count. You start counting spaces on the second number after the decimal. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I have moved 11 spaces. When I have a long decimal, I start on this side and I start counting this way. So I start counting on the number before the decimal, and I want to go 6. So that's 1, 2, 3, 4, 5, 6. And I've moved 6 spaces. Okay. Another way you can do that is this is 12, so I'm going to start writing zeros, and I'm going to count to 11, and this will be my 12th space. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then put the rest of the decimal. Okay, now, here's an example of why you want to use scientific notation. If I were to write this out using all of the zeros, if I have approximately 200 billion stars in the galaxy, and 200 billion galaxies in the universe, and we want to multiply that out to find out how many stars are in the universe, I do 200 billion times 200 billion with all those zeros. Okay, so 200 billion that's millions, 100,000, thousands, right? So I have like 10, 11 zeros, and then I would have to multiply by that by another 11 zero number, and I am going to have 22 zeros at the end. That's a lot to write. But with scientific notation right there, and that's going to be 2 times 10 to the 11th. That's 2 billion. And I want to multiply that by 2 billion. And when I multiply scientific notation, this is how this works. I multiply these numbers, okay, and then I add my exponents. So multiply the numbers, add the exponents. 2 times 2 is 4. 11 plus 11 is the 22. If I'm multiplying scientific notation and I have decimals, I may need to adjust my decimals, and we'll talk about that on another example. Here I have Bill has 60 billion. And John has 200,000. How many more times richer is Bill than John? Okay. How many more times means I'm going to divide. But first I need to convert this to scientific notation. I have 3, 6, 9, 10 decimal places that I need to move. So that's 6 times 10 to the 10th. And then the 200,000, 1, 2, 3, 4, 5. And now I'm going to divide them. So I have 6 times 10 to the 10th divided by 2 times 10 to the 5th. And the first thing I want to do is divide these. Now, in scientific notation, if they don't divide evenly, that's okay. You just get a decimal, which is perfectly fine. And then here, I subtract my exponents because I'm dividing. 6 divided by 2 is 3, and 10 minus 5 is 5. So, Bill is, let's see, 1, 2, 3, 4, 5, 300,000 times richer. Okay. How many times bigger is the number 4 times 10 to the 10th than the number 6 times 10 to the 5th? I'm going to divide 4 divided by 6, and then I'm going to subtract my exponents. And 4 divided by 6 is going to give me a decimal, and it's 0.667, or 0.6 repeating. Now, I can't have this decimal place in the front. I need to fix this. Okay, and to do that I need to move it one place that way. Now, if I am moving decimals this way, I subtract an exponent. If I move decimals that way, I add exponents. Okay, and I add however many spaces I'm moving. So I'm moving one space, I'm moving this way, so I have to subtract 1. So that gives me 6.67 times 10 to the 4th. So again, if I move a decimal this way, I subtract the exponent. If I move a decimal this way to fix it, I add an exponent, or however many spaces. Okay, here's the last one. The national debt was approximately $14.2 trillion in March of 2011. Okay, so 14.2 trillion. The point becomes a decimal or a comma. That's billion, million, 100,000, thousand. Okay, so that's 14.2 trillion. Congress hoped to reduce the debt by 9 trillion. Okay, so there's 9 trillion. And we want to write both of these in scientific notation. Okay, so that's going to be 3, 6, 9, 12, 13 places. So that's 1.42 times 10 to the 13th. And here I go, 3, 6, 9, 12. Okay, now percent decrease is where we're going to divide the change. Okay, so let me write that down. So percent change is equal to the change divided by the original. Okay, our change, and this will be 9 trillion. And I'm going to divide that by the original. So I'm going to divide 9 divided by 14.2. And 12 over 13, so 12 minus 13 is negative 1. I'm going to move my decimal one place here, so I'm going to subtract a 1 from that because I'm moving this direction. And I have 6.34 times 10 to the negative 2, and I want to make that into a percent. Well, to make it into a percent, I really need to turn it back into a decimal. So I'm going to move 2 spaces to the left, so negative 2, so I'm going to go 1, 2. So it's going to be 0.0634, and to make that a percent, 6. Oh, I made too many zeros on here. No, I didn't. Hundreds, thousands, inflation. Okay, no, I was right. Okay, so that's 6.3%. Sorry. The book is wrong, though. When you look on page 244 in the book, that example is incorrect. Okay, your questions for this assignment are, what is a common base? What do you do with the exponents when you are dividing common bases? What do you do with a negative exponent? If I have scientific notation with a negative exponent and I want to convert it to standard, which way do I move the decimal, left or right? And when multiplying two numbers in scientific notation, what do we do with the decimal portion? And what do we do with the 10 to whatever the exponent is portion?